Okay, so now let's see Taylor's polynomial, right? So this is going to be Taylor's polynomial. Taylor's polynomial. This guy here, right? So the Taylor polynomial of a function of degree n at a is going to be the function at a plus the derivative of f at a times x minus a plus the second derivative of f at a divided by 2 factorial times x minus a squared plus and blah 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 up until the nth derivative of n at a, of f at a, sorry, divided by n factorial times x minus a to the n, right? So where does this come from? Okay. So let's see. What we want with the Taylor's polynomial, with what I've been saying before, is we want the polynomial that approximates our function the better, the best we can. Okay, at a. Okay, so we, assuming that f is continuous, right? Let's see how we can build this polynomial. So we have that the limit when x goes to a of f, if f is continuous, is f at a, right? But this is equivalent to say that the limit when x goes to a of f minus f at x minus f at a is going to be 0, right? But remembering what we said before about the small o notation, this means that f of x is f of a plus small o of 1 when x goes to a, right? Because the difference between them is going to 0, right? So that means that our function f can be approximated by the value at a very close to a, right? It's what this means, right? Very close to a, the thing. So f of x is f of a plus something that gets very small when you get close to a, right? But can we improve on this approximation? Yes, we can. If f is differentiable, then we know that the limit when x goes to a of f at x minus f at a divided by x minus a is the derivative, right? And again, we can write this as the limit when x goes to a of f minus f at a divided by x minus a minus the derivative of a at a. All of this, the limit of this is going to be 0, right? We can express this in the same fraction, right? So this is f at x minus f at a minus f prime at a times x minus a, all of this divided by x minus a. All of this is going to be 0, right? So using the small o notation, that means that f is going to be f at a plus f prime at a times x minus a plus, and then you have small o of x minus a, right? When x goes to a, right? All of this is negligible when compared with x minus a when you go to 0, right? And so this is actually the approximation that we had done in the previous unit using the mean value theorem, right? F at x minus f at a divided by x minus a, something like that, right? So that means that if you're close enough to a, your function f is, the value at a plus a line that passes through f at a with the slope that the function has at a. So that means that your function can be approximated by your tangent, right? So if you, for instance, you have something like this, and then you want to approximate this value, the tangent here is going to be something like this. Well, what this is saying is that very close to a, right, the line and the function, the original function, is going to be very similar, right? But now our approximation is better than the one that we had before, because now this is up to an error that's small o of x minus a, right? So the difference is going to 0 much faster than this is going to 0. Okay. Now, can we improve on this better? Can we see if we can do this? F at x is f at a plus f prime at a times x minus a, and then maybe something that multiplies the second derivative at a times x minus a squared plus small o of x minus a squared when x goes to a, right? Can we, sorry, this parenthesis here. Can we do this, right? Can we find this? Well, let's see if we can do this. Can find this limit, right? So what this means is that we want the limit when x goes to a of f minus f at a minus f prime at a times x minus a minus, and then we have yeah, sorry, so yeah, kind of it spoils the ending. So something that multiplies here we want some c that multiplies the x minus a squared, but you will see it will have to do with the second derivative, right? X minus f at x minus f at a minus f prime at a minus x squared, sorry, x squared divided by x minus a squared minus c, right? And let's call this c2 for purposes. All of this has to be equal to 0, right? Because we want this expression to be small o of x minus a squared, right? So this is what we're doing here, right? Now this is equivalent to saying that this limit here, right, is equal to c squared, right? And how can we compute this limit? How can we find c2? Well, for this we have to apply L'Hopital's rule, because this thing is going to 0, this thing is going to 0, this thing is going to 0, right? So if we apply L'Hopital's rule and we find that this limit, the derivative of this divided by the derivative of this, if this exists, then it's going to be equal to this, right? So this is f prime at x, right? And then we have minus f prime at a, right? The derivative of this divided by 2 times x minus a, right? So this is 1/2, and then the limit of this is the limit of the definition of the derivative of the derivative, or in other words, this is the second derivative of x, or of a, sorry, of a f at a, right? So our c2 is this f prime, sorry, the second derivative of a at a divided by 2, right? So now, and so we can try to improve this again, right? Can we do this so that there's a c3 x minus a cube plus small o of x minus a cube when x goes to a, right? So again, we need to write this formula. We want all of this to be f minus f at a minus f prime at a times x minus a minus the second derivative of a divided by 2 times x minus a squared, and then all of this minus c3, all of this we want it to be 0, right? But this again is the same as saying that this limit is equal to 3, right? It's just like using the same argument as before. And then again we need to apply L'Hopital's rule to find this limit. So this is f prime at x minus f prime at a minus, and then we have 2 times but divided by 2, so then we just have the second derivative at a times x minus a, and then we have 3 times x minus a squared. But then again this is going to be 0 again, so we need to apply L'Hopital's rule again. So this is x minus a, and then this is the second derivative at x minus the second derivative at a divided by 3 times 2 times x minus a. And then again we have this as the definition of the third derivative of f at a divided by 3 factorial, right? 3 times 2 factorial, right? So this c3 is this f third derivative of a at divided by 3 factorial, right? And so you can see how we can generalize this argument, right? And keep doing this for higher and higher derivatives, and so we get to this formula that we had seen before in the beginning, right? So we had the polynomial that we want, you know, we can get up to the degree that we want is f at a plus the derivative of f at a times x minus a plus the second derivative of f at a divided by 2 factorial times x minus a squared, and you keep adding, right, the next derivative times the next factorial, right? And so the last term is going to be f to the nth derivative of f divided by n factorial times x to minus a to the n. Right? Now, the interesting aspect here is what Taylor proved, that's what this is called Taylor's theorem, is that the polynomial that we have just seen is f minus the polynomial is small o of x minus a to the n when x goes to a, right? This is just the generalization of this this technique that we have been doing, right? So how do we prove this? The proof is easy, right? We need just to prove that the limit when x goes to a of f minus the Taylor polynomial, we write, you know, degree n at a is going to be small o of x to the a minus n, x minus a to the n. This is equal to 0, right? Now again, we know that at a, these two are going to be the same, so we have to differentiate it, but then we have that, so we have to apply L'Hopital's rule, but the derivative of the polynomial, right, it's going to be, if you think about it, it's going to be start with f prime at a plus, and then we have f at a times x minus a, and then so on. Okay, so all of these terms are going to 0, and then you have f prime at x minus f prime at x. So this is going to be 0 divided by 0 again. So we need to keep applying L'Hopital's rule, and up until when you get to the nth derivative, the nth derivative of x and the nth derivative of the Taylor polynomial. And which this is interesting is that well, not the nth, sorry, the nth minus 1, right, the n minus 1. Okay, so then here, and then here, this is n times n minus 1 times n minus 2 times, you differentiated n times, this is n factorial times x to the a, sorry, x minus a, right? And now what is this, right? So we have the limit when x goes to a, and then we have the n minus 1 derivative of x, and then if you differentiate this n minus 1 term times every term except the last two in the polynomial will vanish, right? So all the powers that's smaller than n minus 1 will vanish. So we have the first term is the derivative, the nth derivative with respect to x of x minus a to the n minus 1. So this is the, right? And this is going to be n minus 1 factorial, right? If you do it again, this is n minus 1 factorial. So this is n minus 1 factorial that multiplies the term that's going with this, which is f to the n minus 1, the n minus 1 derivative at a, right? Now if we compute the n minus 1 derivative of x to the x minus a to the n, this is just n factorial times x to minus a, which is what we have done here, right? Now in the Taylor polynomial, the term that's multiplying x minus a to the n is f to the, so the nth derivative of n divided by n factorial, right? So we have, this is minus the nth derivative of a times x minus a. All of this divided by n factorial times x minus a, right? And so now we have that this is, we can take the factorial out. This is the limit, limit on, the n minus 1 derivative of x minus the n derivative at a divided by x minus a, and then we have minus the nth derivative at a, right? This, I'm just expanding these two things. But this, again, this is the definition of the derivative of the n minus 1 derivative, so this is going to be equal to the nth derivative at a, and this is equal to 0, which completes the proof. Okay, so let's see. Yeah, so just a notation thing, we can sometimes write the Taylor's polynomial of a function like this in a more compact way, right? The kth derivative of f at a divided by k factorial times x minus a to the k, right? That's the compact way, and for this we need to assume, or this is the notation, that this zeroth derivative of f is just f at a, right? And 0 factorial is 1, which is common assumption. Okay. Okay, so let's see one example, right? Let's have f is 1 plus x to the alpha, right? So let's see it's Taylor's polynomial of degree n at 0, right? So we have f at 0 is obviously 1, and then f prime at 0 is the derivative of this, which is alpha times 1 plus x to the alpha minus 1, right? And then this is when x equals 0, and so this is equal to alpha, right? Then the second derivative is going to be alpha times alpha minus 1, right? Times 1 plus x to the alpha minus 2, evaluated at x0. This is alpha times alpha minus 1. And if you keep doing this, the third derivative is going to be alpha times alpha minus 1 times alpha minus 2, and so on, right? You go to, and the nth derivative at 0 is going to be alpha times alpha minus 1 times alpha minus 2 times blah 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 times alpha minus, and then we have n plus 1, right? So this is third derivative 3 plus 1, second derivative 2 plus 1, nth derivative n plus 1. Okay, so now we can write the polynomial, or using the Taylor's theorem, just write the equivalence, so the equality of this as 1 plus, and then alpha times x, sorry, alpha times x plus alpha times alpha minus 1 divided by 2 x squared plus, and keep going, and then we have alpha times alpha minus 1 times alpha minus n plus 1 divided by n factorial times x to the n plus small o of x to the n when x goes to 0. Okay, this is the Taylor polynomial of this function. Okay, now interestingly, this is we can write these terms in a very compact notation, which is derived from the formula for binomial coefficients. So this is the binomial coefficient of alpha divided by of alpha over n, right? So this is alpha factorial times n factorial times alpha minus n factorial, right? This is the definition of the binomial coefficient. Now when you divide these two things, you have alpha times alpha minus 1 times, and then once you start with alpha minus n, all of these terms in the numerator vanish. So this is just alpha minus 1 times alpha minus n plus 1 divided by n factorial. So this is this term here. So there's a very compact way of writing this function, 1 plus x to the alpha, as the sum from k equals 0 to the n of, and then we have alpha over k, the binomial coefficient of alpha over k, times x to the k, all of this plus small o of x to the n. Okay, and this is basically the binomial formula by, so this is Newton's binomial, right? This is what Newton proved in all the way back in 1665, all the way back to there, right? Using derivatives and so forth, he proved this thing, right? The generalization to other functions would come later, right, with Taylor's theorem, but the first one to see this approximation was Newton. Okay, that's the end of the video.